Thanks to the organizers for setting this up and inviting me. So yeah, I'm Eric. I'm a postdoc over at Caltech. So if I seem a little jet lagged, that's why. Uh, so I'll be talking about a paper that was presented at ICLR this year on what's essentially a nice spin glass description of the loss landscapes of quantum neural networks. Um, and I like to think of this result as a solution in search of a problem, because really what I'm most excited for about this work is what can come out of this nice mathematical description. Um, you know, it's nice that we have it now and there are some immediate implications, but I think the real further reaching goal is to see what else can come out of it. So, okay. Before I get into what the loss landscapes of quantum neural networks look like, let me just start with classical neural networks, because the situation is actually very interestingly very different. So just to frame it as a question, I want to first answer, how do neural networks learn? Or to give an operational meaning, how do you optimize non-convex functions over R to the 100 billion in time for NeurIPS or whatever conference is next up on your plate? So, okay, I should say also what I'm about to present is the very, very hand-wavy version. There are rigorous versions of what I'm about to say. But yeah, just to give a sense of what it looks like in the classical setting. So, okay, here I'm just drawing a neural network where, a classical neural network, where each layer, I'm applying some nonlinearity. I call it nu here. There's some input x that feeds into this network. And these lines are the parameters of a weight matrix. So, this is the 1-1 entry of a weight matrix or whatever. And I do p layers of this, and then some output comes out that then you feed into whatever loss function you're interested in. Okay. So there's this paper by Jan LeCun and a bunch of others that essentially says, if you assume these weight matrices are normalized in some way, and you, okay, very hand-wavingly, model these nonlinearities as essentially random dropouts applied to the output of a given layer, you can show that what you get behaves similarly to what's called a Gaussian process. So the output of this network, you can write as some random field on the sphere. So here it's the hypersphere because I just assumed everything was normalized in a certain way. But this manifold might change depending on how you model the normalization. So right, it looks something like this. It's some degree p polynomial of points on the sphere. Okay. And you should think of here n as like the width of the network and p as like the depth of the network. So, all right. So it's known that actually, if you wanted to optimize this, someone gives you some choices of these j, and you're asked to optimize this. Someone can give you, very adversarial choices for these j, and it becomes like a really difficult optimization problem. It's some crazy function. You hope, there's no hope in optimizing it really efficiently. But okay, if this is if these are Gaussian random coefficients, you can ask, okay, how about the typical case? If I just draw this function randomly, is it easy to optimize the typical instance of this? And there, the answer surprisingly is yes. Okay, for certain choices of these weights, I should say, oops, these psi, but modulo some details, it turns out that you can actually just use Newton's method, essentially. So, BFGS kind of techniques, and prove that these find effectively the global minimum efficiently. Okay, you just need the Hessian information to get through some saddle points. But other than that, it's essentially gradient descent. So this, is a nice description of why optimizing classical neural networks is easy. So, I should also say, not only is this model, oh yeah. Oh, psi are fixed. Yeah, J is Yeah, J's are just Gaussian IID randomness. Any other questions? Okay. So it not only has this Gaussian process description, given a nice model of why these networks are easy to train, but also people use these techniques to talk about the generalization performance of these models. This is double descent phenomenon in terms of like overparameterization with respect to the data set, and this you can use to explain that. You can also talk about how neural networks behave as kernel methods in certain regimes. So all of these are essentially based off this Gaussian process behavior of these neural networks. And yeah, here this is some figure showing the asymptotic convergence of what is essentially a histogram of local minima to the global minimum as you look asymptotically, and you're essentially approaching this Gaussian process limit. Okay. So, okay, the natural question then is, oh yeah, sorry. Yeah. Yeah, so what's going on here is, this is from, it was, I think, reference one, this figure. Essentially what they do is they optimize a neural network at a given width. So n hidden you could think of as the width of the network. And they see, okay, when I optimize at a random point, what function value do I end up at? And I do that a million times, and I get some histogram of where I ended up in the optimization procedure. So here the x-axis is like what loss I ended up at, and then the y-axis, it's a histogram. And then as the network gets bigger and bigger, this Gaussian process description becomes better and better, and then it approaches this. I don't actually remember. So what that controls is essentially the locality of this spin glass model. And then n controls the dimensionality. So like the n hidden controls what dimension hypersphere I'm on. I forget what p is, but really to look at the asymptotic behavior of this, n is what matters. So, okay, any other questions? Okay. Oh yeah. Wait, sorry, say again. Oh, double descent. You would have to ask Elias for more details. But apparently, yeah, these like neural tangent kernel descriptions are one way to prove this double descent phenomenon occurs. I honestly don't know the details of how it's shown, so I can't say more than that. But I know Elias knows the details, so this is calling him out. All right. Okay. So yeah, quantum networks, you would want to have a similar universal description, and people, I mean, some people in the audience here have shown in certain settings that you even get Gaussian process convergence for these quantum models. But at least in complete generality, it's kind of a question mark what these things look like. Okay. So just to explain why it's not immediate that whatever you consider a quantum neural network has the same kind of behaviors as classical neural networks. Really, this mapping to a Gaussian process, at least the one I just described, depended on two main things. One is that each of these layers is like a fully parameterized weight matrix. In other words, each of these lines is a parameter that I'm tuning in my network. But typically when people talk about quantum neural networks or whatever, really what they mean is they have some 2 to the n by 2 to the n unitary matrix, and you're doing like e to the I theta poly or something. So you have one parameter for a 2 to the n by 2 to the n matrix. So you don't have this fully parameterized per layer, training procedure. And then two, this mapping relied on nonlinearities. You can show similar kinds of things without the nonlinearities, but at least what I just presented requires these nonlinearities. And yeah, the quantum setting has neither of these two properties. So you got to do a little bit more work to show something here. Okay, I think I just added this slide to be very concrete. So for what I'm going to be talking about for the rest of the talk, when I say a quantum neural network, what I really mean is this parameterized unitary picture. So I have a bunch of unitary gates that have some parameterization, and then at the end I'm measuring some observable. And this figure is from I think this was referenced in the previous talk, an Eddie Farhi and Harbin Nevin paper, but this has been considered in like a VQE context and everything as well. And then I'm really specifically interested in these like VQE kind of loss functions. So you're interested in finding the ground state of some observable or something. Oh, yeah.
Sorry, can you repeat what does it mean for a layer in the classical case to be fully parameterized?
Yeah.
Why is a quantum network with some into the I data needs not considered to be fully parameterized?
Yeah. So typically when you say I have a 3-layer quantum neural network, each of these things, okay, this is a bad example because there are n parameters here, but still, you have n unitaries. So if I look at the unitary matrix on this layer, it's some 2 to the n by 2 to the n matrix, if it's on n qubits. But I'm parameterizing this unitary matrix, in this case with n parameters, or n over 2. Exactly. And so, classically, when you say you have a layer, you have some weight matrix, and PyTorch is doing gradient descent with respect to every, entry of that matrix. So it's a different setting. Okay, anything else? And I just wanted to say, yeah, I'm really only interested in this loss function, and then we can talk about other loss functions later. Okay, I really got to speed up. Okay, so just to briefly review what people have shown about quantum neural networks previously in this specific setting I just talked about. People know you have this famous or infamous barren plateau phenomenon. So generally, if your circuit kind of looks like a 2 design, you expect your gradients to also concentrate exponentially around 0, which makes trading very difficult. But you can also show that in certain settings, if you have some symmetries or whatever, or you otherwise have constrained evolution, that you actually don't have this exponentially poor gradient scaling. Okay, and then on the other hand, in certain settings, you can show that you have really bad local minima. So yeah, I'll discuss this more later, but essentially in typical like feed-forward quantum neural network settings, you're in this under-parameterized phase where you have way fewer parameters than your dimension of your Hilbert space. And so you end up having terrible local minima when you try to optimize. But then also in other settings, people have shown that you don't have poor local minima, and actually gradient descent optimizes perfectly fine, assuming you don't have barren plateaus. And then, yeah, I should add Sofien's talk also to this slide. But there are often cases where you can prove a quantum advantage. And then there are also cases where you can show there are efficient classical simulation algorithms. So I just wanted to point out that people have been looking at little corners of parameter space, essentially, and showing very contradictory results depending on which corner of parameter space they're going in. And ideally, we'd have some unified description of, some global description of these neural network loss landscapes that we can then look at in specific regimes and then reproduce these other results or these older results, and then also hopefully produce new results. So that's what I did in this paper. Okay. So the way I'm going to try and structure this talk, if I have time, is to review briefly what I just said on other work on quantum neural network loss landscapes. And then I'll discuss the main idea behind this work. So really the second section is going to be a tutorial on Jordan algebras, which I hope you all enjoy. And then the third part of my talk, I'm going to talk about the actual implications of this work. So, less the technical stuff and more, okay, so what? All right, so, okay, let's quickly go through this. So I mentioned that there are some issues with a Gaussian process description of these neural network loss landscapes, the quantum case. And the easiest way to see that it cannot be always true that you have a Gaussian model for these things is that there are explicit counterexamples. So for instance, if these unitaries are parameterized in such a way that they look kind of like a T design, they're high depth or whatever, and your O is rank 1, so it's just a projector onto some state, then it turns out this is just a Porter-Thomas distributed random variable at any fixed theta. So this is, they talk about this all the time in like the quantum supremacy papers and stuff. The distribution of the amplitude of a Haar random state is exponentially distributed, not Gaussian. And in fact, it looks nothing like Gaussian. Yeah, and then we know in some situations we have really bad local minima. So, from that alone, it has to differ from the classical setting. And then also there's been a lot of recent work about algebraically constrained quantum neural networks that, like I mentioned very briefly, gave rise to these really nice, you don't have terrible barren plateau kind of results. So, yeah, I should say that in certain settings, you do know that this loss is a Gaussian process. And typically, the setting in which this is the case is that you're sufficiently deep. You have some, random initialization, and your network doesn't have this algebraic structure. And also, your observable is either a Pauli operator or maybe a sum of local operators, like in Giacomo's work. Okay. Well, if we change this a little bit, people have looked at the gradient scaling, not only in like a uniformly random initialization context, but also if you approximately do this. Then also they started considering these algebraic constraints. And then kind of in another setting, more what I had previously looked at, in the shallow networks, again, unstructured. So previously we didn't know how to deal with local minima in this unstructured setting. And then also, at least in this previous work, your observable had to be a sum of local terms. And you had to be very shallow for this to hold. So, okay, I tried to make a little bit of a flow chart. So all this local minima work was in this very underparameterized regime. And then in the overparameterized setting, people looked at gradients in these algebraically constrained settings, and then also showed this Gaussian process limit if you had specific choices of observables and you were extremely deep. And so I claim that all of this can be described by this Jordan algebraic framework. So I call it a Jordan algebraic Weishart system, but really it's a backronym because I wanted to reference JAWS. So, okay, there's some JAWS references in the paper if you want to try and find them. Okay, so now let me talk about Jordan algebras and also Weishart matrices. By the way, I think all the Germans in the audience wince when I say Weishart because that's not how you pronounce it, but that's how I pronounce it, so I apologize. So, okay, I'm gonna ignore all this other stuff and just say, okay, what's the most generic way we can write a quantum neural network, at least of this kind of linear form? Okay, well, really, it's composed of 3 ingredients. So we have some Hermitian observable, O. Okay, it's this math cal H. I just mean Hermitian operators on this field C, so complex numbers, and they're big N by big N dimensional, so think of it as like 2 to the little n dimensional. Okay, it maps to some other Hermitian observable under some automorphism of this, this algebra of Hermitian matrices. And so here this T theta is just conjugation by U of theta, but more generally it could be some other automorphism. And then your loss is some bilinear form, in this case just the trace of whatever O map to with some other row, that might come from your data set. So this algebra or rather this set of Hermitian operators can be made into an algebra if you give it the group multiplication of the anti-commutator. So what I mean by that, or what kind of algebra is this, I should say? It's what's called a Jordan algebra. So people probably know what a Lie algebra is. Like at a high level, you're looking at things like matrices, and your group product is a Lie bracket. So here, instead of taking a commutator, like you do in the Lie algebra case, you take an anti-commutator. But more formally, this product should be commuting. And then also, it's not going to be associative in general, but it should at least be associative if you're taking like a power. So I can split up x to the a plus b in whatever way I want. Okay. And these Jordan algebras show up all the time in physics. So Zoe talked about Majoranas. That's his first Jordan algebra. Also, polymatrices form a Jordan algebra. This very funky looking example is called the spin factor. I don't have to talk about that. But anyways, it shows up all the time in physics. And all of the things I described about automorphisms and blah, 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 can all just be given a Jordan algebraic description. So, okay, what I'm essentially saying here is that any path-connected subgroup of this group of automorphisms, so all of these potential ways of conjugating by unitaries, any subgroup of that, so anything that's closed, is isomorphic to some subgroup of an automorphism group of a subalgebra of Hermitian operators. So that was a mouthful. But essentially what I mean is any subgroup of this automorphism group, so any constrained evolution, you can think of as some automorphism acting on the subalgebra of all Hermitian operators. Okay. So let's go back to our original our original list of ingredients for these loss functions. So now we can think of O as belonging to some Jordan subalgebra of Hermitian operators, and then mapping it under some automorphism of that algebra, and then taking some symmetric bilinear form with some rho, which doesn't have to belong in this algebra, but it turns out you can kind of assume without loss of generality that it does. I won't get into that, but okay, so the nice thing is that all of these ingredients, all of the subalgebras of Hn, and also the automorphism groups and all of these symmetric bilinear forms have all been classified. Like, there are no surprises here. So I can just briefly tell you all the possibilities of what these things could be. So essentially every subalgebra you can write as a direct sum of simple algebras. And each of these simple algebras are one of these three cases. So, okay, the first one isn't so surprising. It's isomorphic to Hermitian matrices over reals, complex numbers, and quaternions. When n is 3, you also have this exceptional case of octonions, but it's only for 3 by 3, so I won't talk about it for the rest of the talk. Also, octonions are really weird, so I didn't want to deal with them. And then also the spin factor I briefly mentioned earlier, but it turns out, so I handled this in the paper. The spin factor case essentially looks pretty similar to the Hermitian real case, so I won't talk about it in this talk. Okay. And then also all of these automorphism groups have all been classified, and essentially they're what you expect. They're all, if each of these are real matrices over some field, Hermitian matrices over a field F alpha, it's either SO n alpha, SU n alpha, or the hyperunitaries. So anyways, you don't really have to know what these are. I'm just saying that they've all been classified. So, you can reduce to one of these 3 special cases, or 4 if you include the spin factor. And then also all of these symmetric bilinear forms are all proportional to taking the trace. So you'll get some proportionality constant that essentially comes from having different representations of the same algebra. So up to this representation dependent constant, they're all just given by the trace. Okay, so put together, what does this tell us? Any quantum neural network is really defined by three things. Some objective observable belonging to some algebra that's one of the Hermitian matrices over a field. So the fields and also the dimensions of each of these simple sectors. And then also the proportionality constant coming from the representation, essentially. And so in the paper, this is a collection of algebraic objects that we just call this Jordan algebraic Weishart system, which again is really just a backronym for JAWS because I wanted to do that. So, okay, let me now explain what a Weishart matrix is. So essentially, you can think of this as like the multi-dimensional generalization of a chi-squared distribution or a gamma distribution. So I can think of some n by r matrix X with IID Gaussian entries. They might be over some field F. And then I look at X times X dagger. So I take this matrix multiplication. So now the diagonal of this matrix will be chi-squared distributed or gamma distributed. And then the off diagonals will look kind of weird, but this distribution over matrices is called the Weishart distribution. And it's an n by n matrix because these x's were n by r. And this r parameter is called the degrees of freedom of this Weishart distribution. Just kind of an analogy with the degrees of freedom for chi-squared distributions. Okay. So I won't get into the proof. It's really just a lot of bounding errors of moments. But what we show in the paper is that asymptotically, if you have some sequence of loss functions and observables and blah, 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 you can show that your QNN loss function defined by this JAWS, this Jordan algebraic Weishart system, approaches this Weishart field. So instead of a Gaussian process, you now have like a Weishart process. And just to explain what all these components are, this I alpha, again, is just some proportionality constant that comes from your representation. If you'd like, you could absorb it into this O bar alpha. This is the mean eigenvalue of O in a given simple subalgebra. And then you also have your initial state projected into that given simple subalgebra. And then this W is a Weishart distributed random matrix over some field, again, given by the simple subalgebras. And its degrees of freedom parameter depends on the spectral statistics of O. Okay, and this R alpha is also what goes in here. Yeah. Yeah, so this is in the wide limit, but with some assumptions on your onsets. So essentially, your circuit has some parameterized, and then sprinkled within those, I'm randomly drawing gates from epsilon approximate T designs that are global. So it's kind of just a model for generic quantum ansatz. Yeah. Say that again? Yeah. Yeah, exactly. So yeah, this is related to the purities stuff yeah, exactly. And then here, we also show all of the moments converge to those of this. So you can get like, yeah, crazier things. So I'll talk about local minima later, for instance. Okay, and then yeah, we can bound the error for this thing. Okay, so let me talk about the implications of this. I should also say, so not only do we have this expression in the paper, but also what we calculate is the joint distribution of F along with the gradient and the first two derivatives, so the Hessian, at any point in your landscape. So not only do you have the distribution of the loss, but also essentially a distribution of the function itself in a neighborhood around any given point. And that lets us look at things like local minima. So okay, yeah, let's talk about implications. So yeah, one of the things that Zoe mentioned is that This looks very similar to what you see in the barren plateau setting. And indeed, if you just look at the variance of this thing, you can look up what the variance of a Weishart matrix is, and this paper shows up all the time in the literature. But one nice thing about what we did here is that we no longer had to assume that this O was in the Lie algebra generating your evolution. So in other words, like I guess one example, people looked at like match gate circuits, and they showed that match gate circuits, if you are doing these projections with respect to Lie groups, you get a different expression for the variance. But if you do it in terms of Jordan algebras, you get the same expression no matter what you pick. So, and then also, we don't just calculate the variance, we look at all the moments. So we have the full distribution. Okay, and then we can also ask, well, when is F a Gaussian process? So, there must be some central limit theorem kind of limit we can take here to make this look Gaussian. So really what we have to ask is, when are these terms Gaussian? And it turns out these are Gaussian essentially when these R alpha go to infinity as n goes to infinity. So do I put it here? Okay, I don't put it here, but if you remember, R alpha is related to the spectral statistics of O. And essentially what this shows is that if O is a sum of local terms, typically you have a very concentrated spectrum of observables that are written this way. And in that limit, R alpha goes to infinity. But if you have something like a GUE matrix or something with a very wide spectrum, R alpha either goes to infinity very slowly or doesn't go to infinity at all. So I talk about this more in the paper, and I don't really have time to get into that now. Okay, so another thing that this lets us do is look at local minima of random loss functions drawn from this distribution. So this is an old paper that's really from 2 old papers with my collaborator Bobak Kiani, where we looked at local minima of, in this case, very shallow, very generic random quantum neural networks. But what this paper allows us to do is look at it even if you have algebraic structure. So, okay, over here, in the unstructured case, essentially what you get is that your local minima have some gamma distributed form, and at least in this underparameterized regime. So this R, again, is related to the spectral statistics of O. And then now, if you have an algebraically constrained model, what matters are the spectral statistics of O in various sectors, like simple algebraic, simple subalgebras of your algebra. And then you take a convolution of these gamma distributions, and then you get some funky looking distribution that might look very different than what you'd expect, depending on how these R alpha are related. Yeah, sorry, this is the expected number of local minima at a given function value. So this expected number looks kind of gamma distributed. Yeah, any other questions? Okay. Yeah.
At some point, how to jump from the randomly initialized model that refers to the distribution picture of the minima versus
Sorry, this picture with the what?
the minima.
Yeah, so this is just looking at the function itself. So the uniformly random initialization, really what I meant was uniformly at random over ansatzes from this distribution, or rather from this epsilon approximate t-design distribution. And then, you have some ensemble of ansatzes, and you can look at the loss function as well as its first 2 derivatives in the neighborhood of any point in your loss landscape. And it'll be distributed in random because your ansatz itself was random. And then you can show, using something called the Katz-Rice formula, what the local minima of your landscape looks like in total by essentially looking at the marginal distributions at all of the points in your landscape of this joint distribution of your loss gradient and Hessian. So it's a lot of words, but really, once you have this joint distribution, you can just turn the crank using this cat's rice formula and calculate what these distributions look like. Yeah, sorry, I had to skip a lot of details for time, but okay, cool. Okay, so essentially what this JAWS framework let us do was, okay, we had these previous local minima results, and then now we can look at these local minima results in a more general setting when you have algebraic structure. Also, we had these gradient results, and we had different kinds of results for match gates and these Lie algebra constrained ansatzes, and now we can look at them under the same lens. And then also, we can completely characterize when you have this convergence to a Gaussian process, at least without dealing with training. That would take a lot more work if you dealt with training. Okay, so I kind of wanted to put this slide in because I've gotten complaints before as someone who works in this field of trainability, of QNNs and everything, that when people in the field say trainable, they instinctively know what they mean, but someone outside the field doesn't really know what they're talking about. So essentially what these results say operationally is that a model class is trainable when you don't have any barren plateaus, according to this like algebraic formula for it. And then also you're in this over-parameterized regime. So sorry, I didn't say what these beta alpha are. These are just some constants that come from your field. Just think of them as absolute constants. But the number of parameters you have has to be sufficiently large with respect to this spectral statistic of your objective observable. Okay. So only 5 minutes late. So yeah, okay, where do I want to go with this? So yeah, just at a high level, what this and other trainability results kind of tell us is that, okay, if we want to look at places where we have a quantum advantage in machine learning, and we don't really know anything about the problem we're given. So, we have results where, okay, we know discrete log is involved somehow, or that it's belongs to some Clifford, some level of the Clifford hierarchy, so you don't have to look through all the unitaries. So outside of those settings, you really need to have some, special cases to get around all of these untrainability results. So for instance, you could look at learning settings beyond VQE. You could look at like classification problems or generative problems. You could ask for some algebraic structure that is hidden to classical algorithms in some way. So for instance, systems exhibiting quantum many-body scars or these other like strange many-body phenomena that we know in principle come from some algebraic structure that we don't actually know what it is. That might be a place where we can look for a quantum advantage in these learning problems. Or maybe outside of training, so we just give up on showing a quantum advantage that includes the training aspects, and then just say, okay, after you've trained your model and you deploy it for inference, that's when we hope to have a quantum advantage. So there's still places where we can look for reasons to use quantum machine learning models, but you have to be a bit clever. Like you can't just blindly apply these models in all settings. Okay, so this is kind of what I said at the beginning of the talk, where really this work is more a solution in search of a problem. But now that we have this mathematical framework for these quantum neural network loss landscapes, we can look at all the problems people have looked at classically for classical neural networks using the Gaussian description in that setting and apply it to quantum neural networks. So for instance, we could look at generalization of these quantum neural network models based off this Weishart process description. We could consider training algorithms that take advantage of this Weishart process description and things like this. And I should also say something that is another interesting potential direction is to use our knowledge of what the loss landscape looks like and how it results from algebraic properties of your system to, from a loss landscape, deduce algebraic properties of whatever system you've constructed your neural network out of. So people have done this more recently. And I wanted to call that out. So, okay, thank you again for your attention. And
Hey,
where you said the conditions that need to be satisfied in order to not have a BP but have a process?
not have a BP, but so this is just oh yeah. So yeah, so Giacomo has looked at circuits that satisfy this for like more classification problems, not really the VQE setting. So that's one example. In the VQE setting, it would be things that are classically simulatable, essentially, or things. Yeah, or you have a lot of algebraic structure, and the sectors are growing to infinity. Yeah, yeah, exactly. Yeah, as far as I know, yeah.
example, like, that are interesting, like, beyond the environment, like, I think with this real general theory of parental, like, basically, invariants are models where invariants are models that they don't show parental, but they are also simulable under some assumption the initial states, and yeah, it's argued that the initial state of the example might be interesting, but is that something from your work that you could say, yeah, like, it's not expansion concentrated?
Oh. Yeah. So, okay, I've given talks on this work before. Do I have a reference? Yeah, so these reference 15s. So you can show that essentially if you look up the Clifford hierarchy, so it's like a generalization of the Clifford group. In a CV setting, you can construct like, depending on how far up the hierarchy you go, you are looking at subalgebras of different dimensions. So at the kth level, it's like n to the k dimensional, or n choose k. And there you can prove that you have a quantum advantage in inference in certain like online learning settings. The issue is, by these results, you don't have an advantage during training. At least you don't have, it might be quadratic or something, but it's not a huge advantage. And the reason for that is by these results, you need a number of parameters growing as n to the k to avoid all these local minima issues and barren plateau issue. Well, barren plateau comes from k being constant. And then, yeah, you need n to the k parameters. So even training these models, I mean, even if it took O of 1 time per parameter, that would take time n to the k, and you can classically simulate this in time polynomial and n to the k. So, okay, during training, there isn't an advantage, but during inference, you can prove there is an advantage. So, it's kind of, it's not free fermions, it's like a hierarchy of bosonic cases that you can show like arbitrary polynomial separations. I don't know if that answered your question. Okay.
Yeah, related. So you were saying at some time that now the good regime is where you have more parameters, like the parameter regime.
Yeah.
What do we mean? So, I mean, can you find a model which is both over parameterized and also easy, like, because you don't want the circuit to be too deep, you don't want
yeah, if you have a lot of algebraic structure. So for instance, yeah, like this free fermion example, you have a parameterized match gate circuit. So essentially it's a free fermionic circuit in the Majorana language that Zoe talked about. It's like quadratic, and those Majorana operators are generated by things quadratic. There, as long as you have like quadratically in the number of your fermions, like n squared parameters, you won't have poor local minima in this setting. And you also won't have barren plateaus because this is a low dimensional subalgebra. But also, if you're just interested in expectation values, it's also classically simulable because it's dimension n squared.
Other questions?
Yeah. It's more like I have this sequence of, you know, O's and U's and whatever. And if the sequence is such that as n goes to infinity, this R, which I didn't write, I might have written once, it's some function of the spectral statistics of O. If this R goes to infinity as n goes to infinity, then I have a Gaussian process limit. Yeah, exactly. Yeah, so like, for instance, this shows up if O is like a sum of local terms. And I'm growing the sum as n goes to infinity.
Okay. Other questions? Yes.
Oh, yeah. Yes, yeah. I have no idea. I imagine it would be similar to your guys' paper, but I don't. Yeah, because you use the fact that like sums of Gaussian stuff, right? Like, yeah, like you could like do the same procedure here, but it would be disgusting. So I think maybe the biggest takeaway is, okay, you know, if you want a limit where we can use what you guys already showed, essentially, look at observables where, again, this function of the spectral statistics is going to infinity as you take the wide limit. So yeah, not only is this sums of one local observables, but sums of k local observables generically, things like this would also have this limit.
Okay. If there are no further questions, then let's thank Eric again. Let's go for lunch, and we